Greetings from the Sea Ranch. This is Nelson Pass with some initial information about the build project called the ACA Mini. The first AMP camp goes back 10 years when a small group of people held the first and only event in Sebastopol, California. I had the privilege of designing this little Class A amplifier, which has proven to be popular among the do-it-yourselfers and which over the years has seen some small improvements. Another AMP camp was planned, but then delayed, waiting for COVID to bugger off. But finally it was decided to go online with it, and once again I have the pleasure of doing the design, something a little different. My goal here is to make a nice little Class A amplifier that is simple and cheap enough to be even more accessible to younger people and technical newbies, but with the performance that will appeal to more sophisticated audiophiles. I spent a couple of hours learning some video editing software, and I shaved my beard for the occasion, so here we go. One of the things I really like to do with audio amplifier design is play with the gain devices. Some audiophiles obsess about wire or capacitors or even resistors, but I find that performance differences between gain devices, tubes, bipolars, and FETs, totally dominates the experience. Pictured here is a simple listing of the four basic types, each having P or N-type counterparts, excepting the tube, where its polar inversion exists in some other universe. Each designer tends to have their favorites, mine being field effect transistors, or FETs, a bit of a cross between tubes and bipolars. I think they offer the most performance in the very simple circuits, and it is my experience that simple sounds the best. There are three ways to use a 3-pin gain device. In this example, an NPN bipolar transistor on the left is common emitter, where the signal goes into the base and comes out the collector with current gain and voltage gain, but with the phase of the signal inverted. Common base mode has the input going into the emitter and coming out the collector with voltage gain, no current gain, and with the signal phase not inverted. Common collector has input to base and output from emitter with current gain, but no voltage gain, and signal phase is preserved. This applies to the other devices as well, with just the pins having different names and with the common pin always grounded with respect to the signal. We will assemble this amplifier from the ground up. We start with a JFET transistor operated in common source mode, having voltage and current gain with inverted output phase. This will form the basis of the input stage of what will be a 2-stage amplifier. Now we add a second stage, a P-channel MOSFET, also operated in common source. With 2 gain stages in succession, we've developed a lot of gain, both in terms of voltage and current. By itself, this would be capable of driving a loudspeaker, but it would be limited in terms of the power and it would have a lot of distortion. We are going to fix those limitations by adding a symmetrically inverted copy of this circuit, where the polarities of all the devices are the opposites. On the top, we have the previous circuit with an N-channel input JFET and a P-channel MOSFET, second stage, and below we have a P-channel input JFET and an N-channel MOSFET. These two halves will operate in a push-pull fashion and greatly increase the output power and also cancel much of the distortion. The circuit now has lots of gain, more than we can use directly, but we will take the excess and use it to improve the performance. Here you see the introduction of a pair of resistors which feed some of the output signal back to the input in a way that lowers the output gain but makes it more like a large version of the original input signal. Here we add some more details, including some part numbers that will be referenced later. This amplifier runs off of a single supply and is necessarily coupled at the input and output through capacitors, C1 and C2. The feedback resistors, R5 and R6, are also capacitively coupled to ground through C4, along with resistors R2 and R3, which provide a reference midpoint voltage. The amplifier output will settle into a DC voltage which is halfway between ground and V+. Resistors P1 and P2 are now potentiometers that will be adjusted to set the idle current of the output MOSFETs. One more element. Because the transistors will drift a bit, or maybe a lot, with temperature, we add resistors R8 and R9 to the source pins of the output stage MOSFETs. Known as local feedback, aka degenerating resistors, they tend to make the two devices more matched and provide ballast to stabilize the bias current. Lastly, we add the details that show the final circuit design. R1, R11, and R12, all 1 k-ohm resistors, are there to prevent parasitic oscillations in the transistors. These transistors are very fast, and if you don't slow them down a bit with these resistors, there tends to be trouble at very high frequencies. R10 and C3 are power supply filters that take AC noise out of the voltage supplied by a 24-volt DC desktop switching supply. R4 and C5 are also power supply filters as well as a timing mechanism for slow turn-on and turn-off. This avoids the thumps visited upon the loudspeakers. R7 at the output is just a bleed resistor so that there are no thump surprises if you connect a loudspeaker to an already running amplifier. You will see the power switch which puts the amplifier in a standby mode where the bias current is shut down so as to not waste power. Finally, we see the values for the feedback resistors whose ratio sets the output gain of the amplifier at 14 dB. Here is a photo of the prototype. The amplifier sits on a single circuit board, roughly 5 by 5 inches, which holds everything but the external desktop switching power supply. You can see the 4 heat sinks for the output transistors and the capacitors for separate supply filters for each channel. Also the output capacitors, plus the connectors for power, inputs, and outputs. The amplifier can be operated as a standalone or it can be mounted in a chassis, which should be well ventilated. And this graphic shows the PC board design, which holds all the parts for both channels plus the connectors and heatsinks. The green traces are on the underside of the 2-layer board and the red traces are on the top. Here is the amplifier from the front. Since this was taken, I added a power standby switch in the center. Now we will talk about the measured performance. To start, here is the graph of the harmonic distortion at 1 kHz into 8 ohms. You will see that the distortion is a fairly straight line between 1/10 of a watt to about 7 watts at a slope which indicates a second harmonic characteristic. The amplifier clips at about 7 watts. Here we see an image of that distortion on an oscilloscope. The top sine wave in orange is the fundamental 1 kHz tone, and the wave below in blue is a magnified view of the distortion embedded in that fundamental. It is nearly pure second harmonic and is time-aligned in what I call a negative phase second, where the negative peaks of the distortion occur at both the positive and negative peaks of the fundamental. Here is the distortion into 4 ohms, and we get a higher but similar distortion characteristic, also up to about 7 watts And above that, we see the addition of significant third harmonic, and then it clips at about 10 watts. Here is the distortion versus frequency at 1 watt, which you can see is flat across the audio band. This graph shows the gain of the amplifier, which is about 14 dB and very flat, all the way up to 200 kilohertz on the top end and rolling off on the bottom at about 2 hertz. That wide bandwidth is further on display with this 20 kilohertz square wave at 2 watts. As noted, this is a Class A amplifier in which both halves of a push-pull output stage conduct current over the entire waveform without the discontinuities seen in Class B and AB amplifiers. In our final graphic, we see an image of the current flowing through one of the output transistors at 5 watts output. The amplifier idles at 12 watts per channel, but enjoys a generous conduction envelope through the square law character of the FETs. You have made it to the end. Thank you for your patience. Final note, I am producing a small run of these kits which will be distributed by the Burning Amp people. Many thanks for their efforts, and also thanks to Linear Systems for donating the input JFETs for these. There is a planned offering for the store at DIYaudio.com, so this will not be your only chance to participate. I hope this video inspires you to get involved with DIY audio. Building your own stuff is really fun and satisfying, which is probably why DIYers are the happiest audiophiles I know. Thank you. Greetings. In this segment, I am here to deliver some thought-provoking experiments with amplifiers and speakers that might interest you. Let's get right to it. About 50 years ago, I visited Barry Thornton of Quintessence amplifier fame, and he showed me a trick for improving the performance of one of the then newly introduced integrated circuits, the 709 op-amp. He externally biased the output stage of the circuit by an external current source, in this case with a load resistor connected to the negative supply. As with many ideas in audio, it's possible that this has been thought of before, but here he gets the credit. It works by adding to the current going through the positive half of the output stage of the op-amp, putting it into Class A, and dominating the output characteristic. As a concept, you could consider attaching that resistor to the positive rail, probably with a somewhat different performance result, being that you can't assume that the output stage is perfectly symmetrical. About 20 years after that, I designed the LF0 power amplifier, which used a complementary output stage paralleled with a large constant current source. The push-pull output stage was already Class A with a heavy bias current, and it already had very low distortion, but I wanted a single-ended characteristic. This DC current source created the asymmetry which gave me the harmonic pattern where the amplitudes declined dramatically with the order, so that third was much less than second, fourth was much lower than third, and so on. A much desired trait that works very well, and I've used this and similar techniques in many power amplifiers. However, as far as I know, I'm the only one doing it, which is fine by me. It occurred to me that an adjustable external current source might be useful at altering the sound of other more conventional power amplifiers, And so I created one to play with, and now I share the idea with you. Here is a simple diagram that shows how it works. You see the amplifier and the load, which is an 8 ohm resistor. These are connected to a signal source and distortion analyzer and an external current source attached to the output of the amp. It doesn't have to be a fancy Hewlett-Packard industrial programmable current source. You can just take a regulated voltage supply and put a large power resistor in series with it. If you want to be fussy, you can use an RC filter at the output of the current source to remove noise and possible distortions that would spoil the cow's milk. But for simplicity, I did not do that here. In this case, I used a 250 watt 74 ohm resistor with a 60 volt variable DC supply and an audio precision S1 analyzer for the distortion measurements. Looking for a good example, I happened upon an old chip power amplifier given to me by Siegfried Linkwitz. I had measured it before, and it was an example of the school of low bias current and high feedback. I measured the distortion at 1 volt output into 8 ohms at 10 kilohertz over a range of 0 milliamps of external bias up to 500 milliamps, and I will show you the progression in 50 milliamp steps in the following little slideshow. Here we see the scope waveforms of the output of the amplifier. The orange trace is the fundamental signal, and the blue is the magnified image of the distortion. Initially, with no external bias current, we see that the distortion waveform is rather large and spiky, having a rather large crossover notch and giving lots of higher order harmonics, our least favorite kind. We will now crank up the bias in 50 milliamp increments. I think you'll agree that was pretty cool. About the time you hit 400 milliamps, the distortion has declined about as far as it'll go in this setup, but higher current doesn't seem to create much of a problem. Just for grins, I also tried flipping the polarity of the current source at 500 mils just to see how it might be different. Here you can see that it has significant second harmonic distortion with that negative phase alignment that I'm always harping on. There are those that might even prefer it this way, and it is worth exploring what we get with both polarities. I performed similar tests on other types of amplifiers. The big Class A amps just shrug it off, and the little Class A amps see a modest difference. The first Watt M2, which is push-pull Class A, without feedback, was hardly affected. Interestingly, there were no improvements to be had by trying this on a couple of cheap Class D amplifiers that I had. I don't expect it to work well with transformer-coupled tube amplifiers, but you never know. And certainly, it will not work with amplifiers whose output is not direct coupled. To a world of audiophiles obsessing about the sound of cables, capacitors, and other things where the measurements do not indicate much, if any, difference, I offer this technique for tweaking. There will be those who say that you should not insert current where the original designer did not intend it. That's a reasonable point, and all cautions should be observed. As fearless amplifier builders, you must accept the risk that comes with playing around with power tools and electricity. That said, not many amplifiers will be damaged by these sorts of experiments, and you never know what you might get. And it's at least as interesting as wooden cable lifters. But wait, there's more. I created the test apparatus shown here, where I can drive a loudspeaker with an amplifier while also injecting it with DC bias current. It's not complicated. You might think such a thing is crazy, but it does give some results. First off, what does the distortion of the average cone loudspeaker look like in this test without any bias current? With a few exceptions, I found that it was second harmonic with negative phase alignment, as in this example. How weird is that? To be sure, I tested the apparatus with a resistor instead of a loudspeaker. And no, it was the loudspeakers. Maybe speaker designers figured out the second harmonic trick long ago. Anyways, following are several examples that I tried. I measured the distortion percentage across the voice coil with the AC voltage at the speaker's resonant frequency and with the amplitude ranging from 100 millivolts to 1 volt AC. This is one of my Moth 8-inch full rangers, somewhat similar to Lowther's. We have a distortion curve with no DC current, which is the top trace, and another with 150 milliamps of DC injected, and we see a reduction in the distortion by about 1/3 with the bias current. Next is a fairly expensive 6-inch woofer with zero current at the top, 75 milliamps in the middle, and 150 milliamps at the bottom, with a reduction of about 75%. Here's a Lowther doing the same sort of thing with 0 to 200 milliamps in 50 milliamp increments, with about a 50% improvement. And lastly, an El Cheapo 8-inch woofer going 0 to 200 milliamps, again with about half the distortion. Now, maybe these aren't massive results, but in an industry where people celebrate tweaks that are barely measurable, perhaps this deserves some attention. What? Did I hear someone say it'll destroy the drivers? I don't think so. If my little Lowthers remain unscathed, then I don't think a couple hundred mils, or about 1/3 of a watt, is going to burn up a voice coil or permanently warp the suspension of your average cone driver. Maybe start with a cheap driver. Another angle, if you have a power amplifier that is DC coupled at input and output, you can introduce this current by driving the input with a little bit of DC offset, giving a larger DC at the output, as illustrated in this diagram. 1 volt DC from an amp's output into 5 ohms will give you about 200 milliamps and will also bias the output stage of the amplifier, possibly killing 2 birds with 1 stone. Let's remember again that there is electricity involved, so caution is advised. As experimenters, you get to take credit or blame for the results. And there you have it, DIYers, a whole new category of audio tweaks. Have a nice day.
Okay, so Nelson, welcome to Burning Amp 2021 online. Are you having fun so far?
Yes, I suppose I am.
We should go ahead and confess to our audience that this isn't live. We've pre-recorded this just to avoid any possible glitches and screw ups and whatnot.
Well, yeah, and also we'll get the pleasure of being able to watch it in real time when it broadcasts.
But that's right. We can just sit back and enjoy. So the first Burning Amp, how many Burning Amps have we had now?
Let's see. The first one was, I think, wasn't it 2008?
I think that's it.
It was the one where I had brought a whole bunch of junk. I loaded up the back of my wife's pickup truck and just loaded it up with speakers and parts and stuff. I basically cleared out a lot of junk, and hauled it down and put it out on tables so that everybody could have it. And so then it was my turn to talk. So I got up in front, and this was in the spot where they hold it now, where they've got a big screen and so on. It's the firehouse. Oh no, it was the firehouse. In fact, it wasn't the North Bay. It was it's the same place we'd been holding it, the very first, and it was in the firehouse at the marina. So I stood up there, and they gave me a Santa Claus hat. I put it on, and I explained to everybody that I had all this junk back there on tables, and they were welcome to it. And I said, the only thing about it is that I can't take any of it home. My wife won't let me.
All right.
Do that. So that was the first one, and numerous people. We had Mark Cronender, and we had Vladimir Simovich, and Stuart Yaniger were the guys who seemed to be running it at the time. Excuse me. And I met the Brocks, Dana Brock and his son Nelson Brock, who was very popular because he showed up with a loudspeaker, which was a Voight enclosure. It's kind of a triangular semi-transmission line. And I think it had a Pioneer, what they call the BOFU driver, which is no longer made, a 4-inch driver with a little tweeter on it. And everybody thought that was just the most amazing thing. It was the kind of thing that going, "Hey kid, are you available for adoption?" And they subsequently then went on to hold the speaker camp in Sebastopol. In fact, actually about 2 miles from where I grew up. This is about 50 miles north of San Francisco over the bridge. And that was a big success. And subsequently, a couple of years later, they held the amp camp. And neither of these events ever got repeated. They were very successful though. But there's kind of an ongoing effort to every year maybe think that they can try to pull something together, but it hasn't happened. But I think it's going to yet. So that was the first Burning Amp Festival, and then they've had it every year except there was one year where there was really nobody to do it, and another year last year, which was COVID, and this year, we've gone online.
Here we are, and we had to learn some new technology and stuff to pull this off. But thank you for doing this. I'm really glad we didn't skip a year. I'm glad we did this.
Oh, I think that would have been going too far. The other thing, as I pointed out, is I think this actually might turn out to be a great benefit because we reach a lot more people with this. We don't have to spend as much money to do it either.
Right. I know a lot of people were disappointed that it wasn't live, and I'm sure we'll get back to that. But I think this, there's no reason we couldn't do the two things in conjunction with each other.
It'll work out one way or another, I think.
Yeah, I'm sure it will. Should we say hello to the Greedy Boys?
Hi, Greedy Boys. We got some stuff for you this time.
Hello, boys.
We might even scrape a little more together before the event.
That's right. So I've had the pleasure of getting advanced copies of your presentations. So let's talk about that ACA Mini a little bit. My first question is this the project formerly known as the Naked F5?
The Naked F5?
You
No, actually, I wouldn't say that because I think it probably actually has more parts. And it's unnakedized by virtue of being a single-ended supply, so it has capacitors on the input and output. So in point of fact, it's not more naked. But I think it brings some really interesting stuff to the table.
So we still have naked F5 to look forward to, perhaps.
Oh, I see what you mean. You're talking about the F5 stripped, which is
yes.
Actually still, it's waiting in the queue. I have, as you know, a list of things that I want to do, and I have the boards here for that, and I just need to finish up some other stuff and then get it out.
Great. Here's a question. Can this little guy, we could run this in lower bias potentially?
The little guy already runs at a slightly lower bias. I'm biasing it at a half amp. Basically it's a 5-watt amp. It's starting to clip at 6, definitely clipping at 7 watts. It's an amplifier that sits on about a 4.5 by 4.5 inch square board, no chassis, little heat sinks that protrude from the top. Actually, if you want, we could pause this for a moment. I can go get it and wave it around. Shall I?
Yeah, okay. Yeah, let's do that.
I'll go get it right back. There. Yeah.
Okay.
So here's the ACA Mini. You can see, I think, pretty well. Okay. It's a svelte little, this is the prototype, by the way. The production boards just arrived. And so maybe later today or tomorrow, I'll be stuffing them up and doing final testing on them. But I've been listening to this now for the past couple of weeks.
Oh, that's true. I'm sure that little footprint's going to be popular.
Well, yeah, and you can mount it on a block, or you can mount it in a chassis, or you can do whatever you like. It's got some standoffs so that it won't actually short out on whatever surface that you put it on, or scratch that surface. But so it got a 24-volt switching supply, and like I said, does almost it does 7 watts. It's just that it's starting to, the distortion is getting out of hand at that point, and it's cute as a bug. It has a really nice second harmonic character to it.
It does. I saw that.
Yeah, and in addition to that, there's actually a couple of little tweaks that can be played with as well that I probably put a little addendum on the project so that people who want to play with it a little further can do so. Because we can roll the harmonics on this by adjusting some resistors a bit.
And the infamous Zen pot.
No, actually, these are power resistors in this case.
Oh, I see. You're changing those.
Because the output devices have got a little bit of degeneration on them for thermal stability. But if you alter the ratios of those two so that, see, that's good. The fans kicked
off. There we go.
If you alter the ratios of the output resistors, plus and minus, instead of having them equal, you can create more or less second harmonic. So actually you can get, you can have more second harmonic, or you can adjust it until it's mostly gone away and get those, even nicer looking distortion numbers. And so it's a tweak, it's got some tweaks available on it. The sum of those two resistors has to remain roughly the same in order to have the thermal stability. This particular one, when you fire it up, I run it at about 2/3 of an amp by it. I'm sorry, not 2/3. It'll be 1/3 of an amp bias. And then as it warms up, it hits a half amp and is nice and stable. So I've settled in something here that'll work well, I'm pretty sure.
That's very cool.
It sounds great. That's what I particularly like about it.
I bet it does. Well, I mean, I'm going to have to get my hands on a copy at some point.
Oh, well, I'm going to be sending you one. I've got, I have 5 or 10 boards, early pieces sitting here right now.
Oh, that'd be great. And some lucky raffle winners today will also be receiving these, right?
We have, I think, 25 going out to lucky raffle winners. If I'm not
Perfect. That's great. And I guess the other question is I hope I'm not telling tales out of school. There's a build camp planned for this? Some kind of online build camp?
I think there is, but I'm not in charge of it, so we'll see how it goes. I think that that's going to be in the hands of 6L6.
Okay. All right. Great. Yes, 6L6. He is. We owe him a debt of gratitude for sure.
Yes, we do. He takes a considerable burden off of me, so that's all to the good.
Yes. That brings me to outside the box. That was a surprise. That was a last minute surprise for me. I thought that was really cool. Would you? I'm a greedy boy too. So, I mean, would you care to expand on the current source that you use there?
Oh, well, I used a resistor. In this case, let's see, as I recall, it was a big 74 ohm power resistor, and I hooked it up to a fairly quiet regulated supply.
Okay.
So, it doesn't have to be a pure current source. It just has to be not something that's, it's got to be high impedance relative to the load, certainly. But the other thing it's got to do is be quiet because you don't want any additional noise. So people can pick pretty much anything they like. In fact, when you get to the second part of that particular piece, you discover that you could use just some offset voltage at the output of the amplifier to send a little bit of current through the loudspeaker, and actually, in some cases, kill two birds with one stone, because the second part of out of the box was not only externally biasing the output stages of power amplifiers and what you can do with that, but also what happens if you apply the same idea to loudspeaker drivers. And so, as you have seen, the characteristics of distortion on drivers and on amplifiers can be altered by playing with this technique. And these are currents that are low enough that they're not going to blow anything up, but in a very few cases, they give startlingly better results, particularly on some of your older, class B, class AB types of amplifiers, and on some drivers. But you start throwing maybe a couple hundred milliamps through, say, an 8 ohm full range driver, something like that, you can have the distortion numbers. And the other thing is, depending on the direction that you send this current, could be plus, could be minus, you can alter second harmonic and play with that. So it's true of amplifiers, and it's true of drivers. Some drivers, not so much. Some actually benefit a lot. But that 50% kind of number was actually pretty consistent. And I went through a range of things. And so this is just a tweak. And there's no guarantee that it sounds better or worse. It is something that do-it-yourselfers can play with at home and see what they get.
The slide that caught my attention most in that presentation was the where you attached it to the speaker and you got the negative phase second harmonic distortion, and which implies to me that the speaker motor favors pulling over pushing, which wasn't intuitive for me. I figured it would be the other way.
I didn't go through a vast number of speaker drivers for this demonstration. So I don't doubt that there are speakers out there that don't have that second. It's been so carefully aligned and it's so symmetrical and so on. And I didn't run into any cases where it was positive, which I assume that, I was surprised that my sampling of drivers all had negative phase second. Now, I immediately went, oh, well, obviously there's something wrong with my apparatus. So I substituted a resistor where the speaker was and measured the stuff and going, no, it's flawless. This is the driver. So that was a surprise. However, you throw enough current into these things, you can change that. And what we were doing was reducing the amount of second harmonic by applying current. And so if we went in the other direction, I did, it'll go more. Now, the other thing is that some of this slightly depends on the orientation of the driver itself. In other words, if you put the driver upside down, or if it's on its back on its magnet versus vertically oriented, how you normally use them, it will be slightly different. But in point of fact, at least in my samples, that second didn't go away. So I knew that it wasn't just how I was holding it. Also, too, you could probably argue that, oh, well, maybe they're being stored that way and the suspension is getting, slowly bent with time and it needs to be just shaken out a bit. That's a possibility. However, I can say also that these drivers were randomly sitting there on the shelf in terms of their orientation, either on their back or on their front. So again, I don't know. But even if that was the case, it's going to be a given that you could probably think in terms of doing this sort of thing and correcting whatever problem you might have. I just look at it and go, well, this is a tweak. You can adjust it. You can play with it and listen to it. Maybe it's better, maybe it's not. But this is where the DIY part comes in. We're not selling a product to you and guaranteeing results. We are postulating that if you try something like this, you might get something that's interesting.
Yeah, I'm wondering if you have a pet theory about why negative phase second harmonic does what it does.
Well, we have Stephen Deere is one of our speakers here at BAF this year, and he's been a mentor to me on numerous occasions because he always has insights that come from the he's an expert in psychoacoustics, and he's the bat guy. He was a bat researcher for, I think, the Navy for many years.
Oh wow!
Doing sonar work, but also he spends a lot of time dealing with the neurophysiology of hearing. So he's going to be a very interesting speaker because I have found him to be one of the most fascinating guys that you could be talking to if you're interested in this. Also, he's going to be a guest here. Well, let's see, this is being pre-recorded. However, by the time you're watching it on BAF, he's going to be in residence at the house here, along with Mr. Full Range, John Verhalen. And so I'm planning on, asking numerous additional questions that always come up. But there are several things that he addresses with regards to the ability to perceive things that aren't normally thought of as being obvious. There's in the case of second harmonic, there's the traditional wisdom. You can't hear phase. And
Helmholtz.
And the fact of life is that in numerous tests, people don't hear phase, but in point of fact, there are mechanisms for phase detection physically within the human ear, but also in terms of the neural networks that gather all this information up. Now, I have my pet theory about all this, and I will tell you about what I think, and that is that the ear is not a microphone. The brain is not a tape recorder. Okay, let's start with that. But what I see is that the ear gathers up a bunch of stuff, whatever it can, and it sends it off to the brain, and there it meets various neural networks. And one of the first things that occurs after the frequencies have been sorted out enough to be routed properly, that the brain begins, what's the word? Let me think. this is where you're going to turn off the tape because I have to think about it for a moment. It is called, oh,
Sure.
I know what it's called. Oh, you can leave that in after all. It's called grouping mechanisms.
Yes.
Neural networks are, they're saying, oh, this goes with that. Okay, these things are related. And so it then takes that conclusion and sends it uphill. And there's more and more of these grouping mechanisms that are assembling things which are attached to each other and allowing for some more conclusions about what's hitting the ear. And the harmonics are clear-cut cases of things that get grouped with fundamentals. In other words, if there's a signal for a fundamental and there's a signal for a harmonic, one of the first things that happens is that the neural network says, oh, those two go together because this one's a multiple of that, and so on. So you have these grouping mechanisms, and they are all operating and going up to hierarchy, higher levels of, shall we say, neural cognizance. And it's all designed to deliver a picture to the brain, to the little man who sits behind your ears, behind your eyes, on the control panel, just like in the cartoons. And he's really fussy. He wants to be presented with a full picture. And so all these underlings assembling all this stuff work very hard to create a full picture for the brain, something that is has a coherent vision of what's going on. And that keeps the brain happy. And if the little guy isn't getting a full picture, he's not so happy. So actually, it's my belief that a lot of the networks down below him will just simply add information that makes it more coherent to make life easier for the little man behind your eyes.
Right.
And I think my personal opinion is that it's a lot of work to make, not only to transmit and assemble the stuff, but then to make up some stuff to add to it so as to keep the guy happy. All of that work translates into the use of energy in the brain, and it is something which can, I think, make you a little on the tired side. And I think that that's part of why people have listening fatigue when they listen to crappy equipment or poor recordings. Their brain is working overtime to, keep the man behind your eyes happy.
So on that note, one last topic for the Greedy Boys. Let's talk about the project queue, starting with, we haven't had an update for a while on the various beasts of various numbers of.
Yes, well, that's reasonably current. Hold on a moment. So, two of the biggest fans for the Beast of 1,000 JFETs are going to be my guests here during Burning Amp Festival. One is Mr. Full Range, John Verhalen, who used to be the Lowther distributor in the US and now is the Cube distributor. And the other is Stephen Deere, psychoacoustic neurological expert of our age. They both were huge, still are, huge fans of the Beast of 1,000 JFETs. To explain what that was very briefly, it was all these tiny little wonderfully great Toshiba JFETs that are so difficult and expensive to obtain. And I always had wanted to see what they sounded like as a power amplifier device. And so I paralleled them up in a complementary output stage, and it was run balanced, and it came out to be 1,000 JFETs per channel. These days, that would mean something on the order of $10,000 to $20,000 a channel for parts. However, I have more recently experimented with other JFETs, trying to get them to do a comparable job. And I managed to, get some decent approximation for that in small prototypes. And right now, Stephen Deere is using one as a headphone amplifier, I believe. In any case, but so I was encouraged to actually think about, tackling this thing again. This is 1/2 of a channel. You can see at the top that I've actually started stuffing the transistors in
Yes.
that, and you can see that them all in that little row there. This by way of putting together. I'm testing. Actually, I'm testing the artwork because I send artwork off and I sometimes make mistakes. So I've learned not to, put 1,000 transistors on a board until I've confirmed that at least some of them work. And
Good idea.
See, all the resistors have been stuffed that way. Being that they only cost about a penny each, I'm not real worried about them. So at this moment, I'm assembling 2 pair of channels of the beast. And if it works out as well as I think it will, then it actually could be a project where people could build their own. Because fortunately, in this case, the Fairchild / Onsemi transistors involved are fairly inexpensive. They have to be selected, and there's a lot. Mostly, though, it's a lot of labor. When you're soldering 1,000 transistors and a comparable number of resistors into a circuit, then it's a very labor-intensive proposition. But yes, the beast is on its way.
I understand. And of course, you mentioned that we've got some big sit stuff to look forward to.
Yeah, might even have something in time for this presentation at Burning Up, at least in terms of a, hand waving. Here's a picture of it. And this is what.
Good.
Because the sit light, which is an SIT, big hockey puck SIT that I've encouraged people to buy, coupled with a 300-watt light bulb, that's an amplifier. It may or may not be everybody's exact idea of what they want, but it gets people started in terms of playing with these parts. And right now, there's some guys, I think, sitting around with these parts, going, oh, what am I going to, I got to do something with it. Well, here's something where you can get started. You can always take these out of that and put them in something else later, precious as they are. Those are rugged parts. They will survive.
Yes, they are.
Oh, unbelievably rugged. Everything else, everything else burns up.
Anything else on the DIY front to cover?
Oh, on the DIY front, let me think. Oh yeah, well, I got some stuff. Let's see, we've got the ACA Mini. I had a conversation with Jason at DIY Audio recently, and we were talking about they have the B1 Korg kit at DIY Audio, which has a nice little chassis. It's got 2 sets of inputs for a preamp and an output and a volume control and a switch. What more could you want? And it's a nice little chassis. It's all made and everything. And people are swapping circuits because the chassis is useful. The B1 is not the only thing. The B1 Korg is not the only thing that could go in there, says I. I decided that what we want is a motherboard that fits nicely into that chassis, has all the input-output connections in the pot and everything all wired up nice and neat, and just simply requires a plug-in board for a pair of channels. And then once you've got that, the DIYers can build kit after kit after kit of trying different circuits.
I like that.
And stuff that you see Mark Johnson doing that sort of stuff. Wayne is capable of doing that sort. Even I am capable of doing the odd preamp. And the idea here is that you can play with all sorts of things. You don't have to buy a whole new chassis and everything else. It becomes a modular in terms of its construction. And I just think that would be terrific because the cost, I mean, most of the costs associated with these kits are the chassis and such, and the power supplies. You get past all of that hardware and you're down to just a few bucks. So
That's I think that's a great idea. I might even do something for that. I like it.
The goal of this guy was to build a sweet amplifier that doesn't cost a lot of money. If you look at the ACA as a fine example, most of the money is in a chassis and associated with hardware, which from my standpoint is not really the essential interest part. This is on a PC board. It doesn't need a chassis. It's got some connectors on board. It's got these little heat sinks. Now the heat sinks are on the board. The heat sinks are the most expensive part. They cost $4, $5. So, but you add all that up and you can offer an amplifier at what hopefully be very reasonable price through the store, and it pops right together. It's kind of in the vein of the ACP that happened a couple of years ago.
Yeah, I have one of those. I built it on a nice Baltic birch plinth. I love that thing. I love it. I think it sounds great.
One of these, and you can get yourself a nice piece of birch and plinth it up.
Absolutely. So I just had a random thought. Let's start a YouTube channel.
Yeah.
Okay.
Well, we discussed this. Past DIY is available. That's a nice name for a YouTube channel.
It is. It's perfect. Nelson, I want to thank you for hanging out in my listening room and letting me hang out in your lab. And I think you and I need to get ready to head over to a Q&A just about now. So thanks for coming to Burning Amp Online 2021.
Well,
thank you, sir.
Before I say goodbye, I explained to the audience that, of course, we pre-recorded this. Today, he and I were supposed to get on Zoom and just talk about doing this at some later point. And we kind of got going with, well, why don't we just keep on with it, hope that it's good enough with a little editing, it gets turned into the real thing. And we don't have to do it.
That's right. The magic of editing.
Now, you see, that's why my hair's not combed and my shirt is, all, needs an ironing is what it needs. But, at least you get to see us how we really are. So, it's been a pleasure as always, Mike.
Same here, Nelson. Thanks a lot.
Thank you. I'll talk to you later.
Bye. Stereo file, November 1991. And inside is your interview with Tom Norton.
That was when I was still with Threshold.
You were still with Threshold. That's right. I think you were, it was towards the end of that period of time.
I was on my way out.
You were on your way out. And so if I can find it here, I'm pretty sure that a young Mike Rothacker went to Las Vegas to CES, and there it is. Can you see that? I got an autograph.
Yes. Oh, well, amazing.
Look at that. And we got to talk for a while, and it was a big deal for me. And then a couple of your bodyguards dragged me out of the room and took me out in the desert left me with a jug of water. So it was a great show, though.